Healthy coral reefs provide excellent protection against waves. Although they are brittle and you can easily snap off a piece of coral, they're really good at reducing wave energy. Unfortunately, coral reefs are in decline worldwide, and we're starting to see the impacts of this decline. Traditional coastal protection measures focus mainly on wave attenuation. They're hard, strong, durable, hold very limited potential for reef restoration or reef development. This works really well if wave attenuation is the only function we should look at, but unfortunately the world is more complex like that. And we believe that artificial reefs should incorporate as many functions as possible in order to fulfill a societal need. In vulnerable remote locations, materials for traditional coastal protection measures need to be imported from the mainland, and this puts even more pressure on the climate, on the reefs and on resources in general. In tropical island nations where ecotourism is developing really fast, traditional coastal protection measures may no longer be sufficient. Guests want to experience a healthy looking reef with fish instead of concrete blocks with no coral communities on them.
In the next 2 weeks we will be testing our structures in the wave flume at Deltares. Coastruction has been granted the SME voucher and therefore they can have 2 weeks of free testing in the wave flume, the Scheldvloem here at Deltares. So we are very excited to be doing that the coming 2 weeks. And during these tests we want to find out whether structural complexity of coral reefs have an influence on the wave attenuation. Coral reefs work as a natural coastal protection, since they dissipate the waves, and they do this via wave breaking as well as via frictional dissipation. And this second term is of our interest, because the frictional dissipation is a result of the roughness of the reefs, and the roughness of the reefs are a result of the structural complexity of the reefs. This is something that we are going to test in the wave flume with testing 2 or 3 different designs with different complexity levels. In this research we will quantify structural complexity using 2 different parameters. The first one is porosity and the second one is rugosity. Porosity is some sort of a parameter which quantifies the ratio of void to volume, and this has been computed online in a software. And the second parameter, which is called rugosity, we have measured using a so-called chain tape method, which has also been used in nature. And this is a method where they use a chain with different links, they lay it around the corals, and then they measure the distance of this chain with, they divide the distance of this chain with the linear distance of the chain. Coming 2 weeks we'll be testing these different structures in the wave flume, and we'll be doing this by placing them in a reef formation in the flume, which is a 1-by-1 reef. And we'll be performing tests with many different wave conditions, and we will then measure the wave heights in front of the reef as well as in the rear end of the reef, and we will then compare the wave heights with each other and see what the difference is. We will also measure the flow velocities on top of the reef as well as below the reef, within the reef, to see how the water and flow behaves with these different designs and structures. So we are very excited to see what the results will be for the coming 2 weeks, and let's start.
Those are our 3D printed structure, and we 3D print them all with the Coastruction small 3D printer Idefix. We printed with local material from Rotterdam, local sand from Rotterdam River, and marine cement. We designed the structure together with our advisory board experts David Lennon, and we kept in account the power of our technology to be able to allow us to 3D print complex and natural looking shapes. While designing this, we keep in mind the multiple functions that we want to address in the same structure. As you can see, the design has these ledges that are super important for permit the corals to grow and also the larvae of the coral to settle and grow later. We kept in account all the small and big fishes and marine life that they need cavity and swim through and complexity in the shape. we have a strong bottom where you can pass a sling or a rope, and then you can install your structure in an easier way. Also keep in mind stability, because it's very fundamental for breakwater's function. So the top part will always be lighter than the bottom part of the design. To prove that complexity as an influence in wave attenuation, we designed 3 levels. We start with the first one as a reference, as a cube, and then the second one we're gonna increase the rugosity, and the third one we're gonna increase the porosity. So we can see how different complexity reference can increase or modify the effect of the attenuation of the waves. Of course, this is a scale model and this is a scale test, so you need to imagine this structure has a 1 cubic meter in reality. Nowadays, solution for coastal protection, they don't really keep in mind the biodiversity needs of different environments. But at Coastruction, we do, and that's why we are doing this test. And this is gonna allow us to provide a solution of artificial reef that they can address the function of coastal protection, but also biodiversity needs. And we can custom made any solution and any design for different specific environments on the planet.